Hello everyone, welcome to this recorded version of lecture 3 in MA 283 linear algebra. So the live version of this lecture will take place on Wednesday, January 19th at 1 o'clock in RC Cahal. This recorded version is for anyone who can't make it there or who'd like to have a chance to review the video version later. Okay, so we're still in our review of matrix algebra in chapter 1 of our lecture notes. We're in section 1.2. And we're just going to pick up the discussion where we left it off last Friday on the definition of and mechanisms of matrix multiplication, which is quite a complicated arithmetic operation and has a definition that looks potentially a bit obscure the first time you see it. So really the point of today's lecture is to try to give a couple of interpretations to demonstrate how matrix multiplication is actually sort of a sensible, well-defined operation that captures important phenomena of both geometry and algebra. Okay, so our setup is, we've defined, on Friday we talked about how to multiply a matrix by a vector, provided that the number of columns in the matrix is the same as the number of entries in the column vector. So if you've got a matrix A and a column vector V, then the product AV is the linear combination of the columns of A, whose coefficients are the entries of the vector V. So we can do this as long as we have the same number of entries in V as we have columns of A. And so it's just the first entry of V times column 1 of A plus the second entry of V times column 2 of A, and so on. So it's a vector with a single column, and the number of entries that it has is the number of rows in the matrix A. Okay, so if we wanted to find a pair of the product of a pair of matrices generally, then it's really kind of a small extension from that. So suppose we have a pair of matrices A and B, and the conditions that we have on A and B is that A is an M by P matrix. So it's got M rows and P columns, or another way to say it is the number of entries in a row of A is P, and B is a P by N matrix. So the number of entries in a column of B, or the number of rows of B, is P, and the P here in A is the same as the P in B. So provided that those two parameters agree, we can define the matrix product AB. And what it is, basically, is it's a matrix with M rows, so the same number of rows as A. That means each of its columns has M entries. It's got N columns, so the same number of columns as B. And the columns of this product are just the columns of B multiplied in front, respectively, by the matrix A. So the first column of the product AB is the linear combination of the columns of A, whose coefficients are the entries of column 1 of B. Second column of the product AB is the linear combination of the columns of A, whose coefficients are the entries of the second column of B, and so on. Okay, so just think about this in the context of the matrix vector product and write down a couple of examples for yourselves to satisfy yourself that you agree. Okay, that's how matrix multiplication is defined in terms of the operation of matrix vector multiplication that we saw on Friday. In terms of actually kind of practicing the operation of matrix multiplication, I guess, like actually calculating the product of two matrices, which is not the only thing we want to do, but we do need to be able to do it. In terms of that, it's not always in terms of matrix vector multiplication that we think about it, although it's a very good way to think about it conceptually. So just a remark for a couple of reasons about the entries of the matrix AB. And one of the reasons is to highlight the last line here and to sort of make sense of the notation that's used there. Okay, so matrix products are often presented and explained just in terms of their individual entries, which is kind of practical if what you want to do is calculate with them, but somehow kind of I think can sort of risk losing out on some of the important conceptual meanings of matrix products. So, but suppose that you did have an M by P matrix and a P by N matrix AB, just exactly as in the definition there, and their entries are in some field. And suppose you want to describe what is the entry in row I and column J of the matrix product AB. So a bit of notation, first of all. In general, for any matrix A, the entry in row I and column J of A is denoted by A subscript ij. The position that's in row I and column J is referred to as the ij position. And the only thing to kind of bear in mind there is that the I, which comes first, labels the row, and the J that comes second labels the column. Okay, so in the matrix product AB, defined as in definition 5 there at the top of the slide, the entry in the ij position of the product AB, okay, that's in column J of AB and in row I. So column J of AB is a linear combination of the rows of A pardon me, column J of AB is the linear combination of the columns of A, whose coefficients are the entries of the jth column vector in B. So it's the linear combination of the columns of A, whose coefficients are the entries of the jth column of B. Okay, so this is the linear, so the entry then in position ij is the linear combination of the ith entries of the columns of A with coefficients from column J of B. Okay, and what that exactly is it's the entry AI1, so the first entry in the ith row of A, second entry in the ith row of A, up as far as the pth entry in the ith row of A. Each of those guys is multiplied in turn by the entries in the jth column of B, which are B1j, B2j down to BPJ. So the entry in the ij position of the product AB is this product. It's AI1, AI2 up to AIP. These are the entries of row I of A. Multiplied in turn by B1j, B2j down to BPJ. These are the entries of column J of B. And so basically, the ij entry of the matrix product AB is assembled from the ith row of A and from the jth column of B by taking the first entries, multiplying them, second entries, multiplying them, and so on, and then adding together all those products. And so that, of course, can be done as long as the number of entries in a row of A matches the number of entries in a column of B. And finally, just if you have a second, give your attention to this sort of description here at the end, which is a shorthand and compact and convenient way to describe what's written to its left. This is the sum as k goes from 1 to p, so as k basically runs through the entries of a row of A or of a column of B, of the expression aik multiplied by bkj. So the I and the j are fixed here. We're talking about the ij entry, and the k is an index that runs through the entries of a row of A and a column of B together. So it's the sum over k from 1 to p of the expression aik bkj. Okay, that is another description of a matrix product. Okay, so in the definition above, it's the matrix product of two matrices is defined as a sort of a combination of matrix column products, and then the second half of the slide is kind of just taken up with an explanation of what exactly is the entry in the ij position of the matrix product AB. Where does it come from? It comes from the ith row of A and the jth column of B. And something that I just mentioned here, although it probably is relatively obvious anyway, is that, when you think about the content of this slide and how the entries of AB are assembled, it's pretty clear, I think, that even if the product BA is also defined, which would require that the M here is equal to the N, which is not necessarily true, but even if it is, so if the products AB and BA are both defined, they're certainly not equal to each other, because in the same way that the entries of AB are assembled from rows of A and columns of B, the entries of BA are assembled from rows of B and columns of A. So they're not going to be the same thing in general. Occasionally they are. That's an interesting thing when that happens, but it doesn't happen typically. Okay, so since we're on the subject, let me say something about matrix multiplication in connection with the scalar product of vectors, which is something that you are familiar with already, at least in Euclidean spaces. So basically, in our previous slide, we had a matrix A whose size was n by p, and a matrix B whose size was p by n, and we were looking at their product, which was an m by n matrix. And the remark is that the calculations that we do for all the entries of AB is actually what they call a scalar product calculation. So here's a definition. So if U is a vector and V is a vector, both with p entries, with entries in some field F, which we can take to be the real numbers, for instance. So U is a vector with entries A1 to AP, V is a vector with entries B1 to BP. So think of them as being vectors in R2 or R3. Then the so-called ordinary scalar product. We're going to have other scalar products in the future which are not as ordinary, or the dot product of U and V, is the element of the field. So it's a scalar, which is why it's referred to as a scalar product. This thing is not a vector, it lives in the field. So it's a real number if we're working over the real numbers. And it's the number that you get by taking the first entries of u and v, multiplying them, second entries of u and v, multiplying them, and so on, multiplying together all the entries of u and v in order, in pairs, and then adding together all those products. So it's the sum of AK, BK, where k runs through the entries 1, 2, 3 up to p of both u and v. Okay, so that thing is the scalar product. And we know that, for example, if we're in R2, we've been calculating these things for a long time. If we take the vector 1, 2, and the vector 3 minus 4, let's say, in R2, then the scalar product of those two vectors is 1 times 3 plus 2 times minus 4, so it's minus 5. And we also know that in R2 or R3, or Euclidean spaces in general, u dot v has a geometric interpretation. It's the length of the vector u, meaning the distance from the point whose coordinates are the coordinates of u to the origin in R2, times the length of the vector v, times the cosine of the angle theta in between u and v. So the picture's like this. Here's R2. There's the origin. There's u, maybe. There's v, and theta is the angle in between them. So the scalar product has a very interesting geometric interpretation in real vector spaces. It captures information about the lengths of vectors and the angles between them, which is one of the reasons that it's interesting. In general, over some field, we may not quite have this interpretation in terms of lengths and angles, but even so, we have a concept of orthogonality. And we know that in general, if we're in R2, and u and v are two non-zero vectors, then if their scalar product is 0, it means the angle between them is pi over 2 or 90 degrees, or it means the vectors are orthogonal to each other, that the angle between the line segments represented by them is a right angle. So as long as u and v are not the 0 vector, in R2 this is true, that the idea that the scalar product is 0 exactly if the two vectors are orthogonal to each other. So in general, in any setup where we're not necessarily working in one of these Euclidean spaces, we say that a pair of vectors are orthogonal to each other with respect to the scalar product if their scalar product is 0. And later we'll have multiple different examples of scalar products, and we can have orthogonality with respect to one scalar product or another. But the remark for now is just that if a pair of vectors in Fp for some field F have the property that when we calculate this their scalar product in this manner, we get the 0 element of our field, then we say that they're orthogonal to each other. And if our field happens to be the real numbers, they're orthogonal to each other geometrically in Euclidean space. The directed line segments that represent them are perpendicular to each other. Okay, why are we talking about this in the context of matrix multiplication? Well, just looking back at the content of the last slide again, if we think about it again, and we go back to our m by p matrix and our p by n matrix. So the picture here, A is m by p. So we've got m rows in A, and each of them has p entries. In B, so this is our matrix A. This is our matrix B. It has n columns, and each of them has p entries. And AB is going to have m rows, same number of rows as A, and same number of columns as B. So the P has kind of dropped out of the size here in AB. But what happened to the P, I suppose, if anything has happened to it, is that when we calculate an entry of AB, we're taking a scalar product of a vector with P entries, which is a row of A, and a vector with P entries, which is a column of B. So for example, if we want to know the IJ entry in here, so let's say here we have row I and column J. So here is the IJ entry of AB, and what it is the scalar product of row I of A and column J of B. each of those things is a vector with p entries, and their scalar product is the entry that goes into the ij position of the product AB. So another way to think about the matrix, the product of two matrices, A and B, is that it's like a table of values of the scalar products of rows of A with columns of B, in the sort of obvious configuration that in the first row of the product, you have the scalar product of U1, the first row of A, in turn with each of the columns of B, and so on. In the second row of the product, we have scalar products of the second row of A with the columns of B in turn. So that's another way to think about matrix multiplication. It's kind of like to think about the product of two matrices, I guess. It's like a table of values of the scalar products of rows of one matrix with columns of another. And of course, for that to make sense, the number of entries in a row of the first matrix has to be equal to the number of entries in a column of the second one. So that's a way of thinking about the matrix product. I'm not saying that one of these is the right way to think about it. I'm saying that we kind of enrich our vision of what it means by having all these different interpretations. And there are two more of them coming in the remainder of this lecture. Okay, so I guess having said all that, it's still not really completely clear how one would come up with the definition of matrix multiplication if you were sort of handed two matrices and asked to figure out what it should mean to multiply them. So I just wanted to give an example of another type. And this is an example where the matrices that appear are kind of tables of data. And certainly more and more so, we are living in a world that's full of data and tables of numbers that come from different scenarios and different observations. I'm not saying that every matrix is a table of data. I'm saying that tables of data are a sort of source of matrices that are of potential interest in things that we want to understand and things that we want to know about. And even so, okay, so matrices, obviously, they're tables of numbers, but they also have all their own kind of life in terms of their own algebraic properties and their interpretations of different parts of mathematics and their links to geometry and so on. So it's not necessarily automatically true that every table of numbers that you encounter coming from, let's say, some kind of real life data or whatever, necessarily is interesting when it comes to kind of thinking about it as a matrix and applying the operations of matrix algebra to it. But the surprising thing, in my opinion, at least, is that sometimes they do. Sometimes even if a matrix just kind of comes from a table of data from some ordinary everyday thing, it still actually turns out that the operations of matrix algebra have a meaning and an interpretation that makes sense in terms of that data. And this example is kind of meant to illustrate that. And I want to kind of not oversell this. I'm not saying that every possible instance where you come up with some examples of tables of data will always have these kind of properties. It's not necessarily true, but one can make up stories where the products do make sense. So the story here is that we have a university. It's called Eigen University. And we have on the top left here, we have a table. And Eigen University has three subject areas. It has humanities, it has engineering, and it has science. And the table here at the top left is the table that shows the number of first-year students in each of these areas in the 2 years, 2015 to 2017. Okay, so it's just a table of data. Whether you call it a matrix or not is kind of up to yourself. But certainly we can extract the information in this table, the sort of 3x3 numbers there, and call that matrix A. Okay, so the rows of A list the numbers of first-year students in the three subject areas in 2015, 2016, and 2017. Okay, so there they are. And the columns of A correspond to the three subject areas, humanities, engineering, and science. Okay, that's fine. So we can give the name A to that matrix, which has that, the numbers in that table. Okay, the second ingredient is that every first-year student at this university takes either linear algebra or calculus. And depending on what subject area you're in, you might take more or less linear algebra or calculus. So the second table shows us, for the students in humanities, engineering, and in science, how many credits they take in linear algebra and in calculus. So the humanities students, for example, take 10 credits in linear algebra and they don't take any calculus. The engineering students take 15 in each, and the science students take 20 credits of linear algebra and 10 credits of calculus. Okay, so again, we can pull out that information and give it a name, call the matrix 3x2 matrix that contains that data, call it B. Okay, so that's fine. That's just a made-up story about a fictitious university. One thing to note is that the labels on the three columns of the 3x3 matrix A are the same as the labels on the three rows of the 3x2 matrix B. Okay, so in A, the columns are labeled by humanities, engineering, and science. In B, the rows are labeled that way. And the other thing to notice, I suppose, is that A is a 3x3 matrix and B is a 3x2 matrix. So the product AB does exist. We can multiply a 3 by 3 by a 3 by 2, and the result of that would be a 3 by 2 matrix. So let's do it. So the sort of advice there at the end of the slide is look at the meaning of the entries of the product AB. So let's do that and see what we discover. I'll try to get the multiplication right. I have a high probability, of course, of getting it wrong, but let's see. Okay, so here are our matrices A and B. So A is 3 by 3, B is 3 by 2. Their product should be a 3 by 2 matrix, and to work out what its entries are, well, the entries in the first row of the product come from the first row of A combined with the columns of B. So in the top left, we've got 50 times 10, that's 500, plus 100 times 15, that's 1500, so 2000 so far, plus 70 times 20, that's 3400. In the top right, we've got 50 times 0, plus 100 times 15, that's 1500, plus 700, that's 2200. In the second row, we've got entries of row 2 of A combined with the 2 columns of B. So we've got 600 times 10, plus 80 times 15, that's 600 plus 1200, plus 80 times 20, that is 1600. So we've got 3400 in total again. In the second entry of row 2 here, we've got 60 times 0, plus 80 times 15, that's 1200, plus 80 times 10, that's 800, so 2000 in total. And in the third row, we have the third row of A combined in turn with the 2 columns of B. So in the lower left, we have 80 times 10, that's 800, plus 70 times 15, that's 1050, so 1850, plus 1400, 3250. The numbers are not so important. But then finally, in the lower right, we've got 80 times 0, plus 70 times 15, that's 1050, plus 700, so 1750. Okay. Okay, so the assertion is that in this example, these numbers really kind of mean something. So let's see if we believe it. And to address that, let us recall what the entries in the table described by the matrix A were. So the rows and columns of A. The rows of A were labeled by the years 2015, 2016, and 2017. And the columns of A were the numbers of first-year students in humanities, engineering, and science at Eigen University in each of those 3 years. In B, the rows were labeled by the humanities students, the engineering students, and the science students. And the columns were the number of credits that each student takes in linear algebra and in calculus. So a student in engineering, for example, takes 15 credits of linear algebra and 15 credits of calculus. Okay, so when we take this product AB then, what are we looking at? Well, the top left entry of AB, let's look at that. Where did it come from? Well, it came from 50 students in humanities in 2015, taking 10 credits each of linear algebra, plus 100 students in engineering in 2015, taking 15 credits each of linear algebra. That's a total of 1500 linear algebra credits taken by students, plus 70 students in science, each taking 20 credits of linear algebra. So that's another 1400 linear algebra credits. So the 3400 here is the total number of linear algebra credits taken by students in 2015 in humanities, engineering, and science. Okay. 3400 here, similarly, is the total number of linear algebra credits taken by students in humanities, engineering, and science in 2016. And the number in the third position there, in column 1, is the total number of linear algebra credits taken in 2017 by first-year students of Eigen University in these 3 subject areas. So basically, AB again gives us a table, and what labels the 3 rows of this table are the years 2015, 2016, 2017, same as the labels in the rows of A. And what labels the columns here are linear algebra and calculus. And the entry in the IJ position is the number of credits taken by first-year students in the year that labels row I of A or of AB in the subject linear algebra or calculus that labels column J. So for example, the 2000 here, just a final example, that's in the row labeled by 2016, and it is in the column that labels calculus. So it's the total number of calculus credits taken by students in 2016 who were in their first year of their studies in Aigen University, either in humanities, in engineering, or in science. Okay, so I'm not saying that every example where you can sort of label the rows and columns with some kind of information coming from some pretend realistic scenario, that the matrix products will always make sense, but there are cases in which they do. And our first weekly challenge, which is now open on the Blackboard page, is to come up with another example along these lines of some pair of matrices corresponding to data from some made-up story, or some real story if you like, in which case the matrix product and its entries also make sense in terms of this story. So even in the business of putting together arrays of data that come from information that's around us, the operation of matrix multiplication sometimes has an interpretation in that context, and that really is the point of this example. Not to say that it always does, or that every matrix product can be interpreted that way, but that sometimes it does, and it's actually something that's useful and relevant in various areas that involve analysis of data. Okay, and our last item for this lecture is another interpretation of matrix multiplication in terms of some more objects that are important in linear algebra and in geometry, and those are so-called linear transformations. So the reason for introducing this now is because it is a linear transformation is another very important fundamental object of linear algebra, and we are interested in sort of this first chapter is kind of a preview of all the things that we're going to be exploring in more detail, and linear transformation certainly falls into that category. And also because this is another interpretation of matrix multiplication, which is really important and very robust, and applies to all examples of matrix multiplication, unlike the last one about potential cases where arrays of data can make sense as matrix products. This is one that applies all the time. Okay, so generally speaking in mathematics, we are interested in functions. We're interested in sets, maybe with some certain properties, and we're interested in functions that go between them. And sometimes when we're doing algebra in particular and dealing with structures like vector spaces that are defined according to certain principles, we're interested in functions that sort of somehow preserve or respect those principles. And an example of that in linear algebra is a linear transformation. Pardon me, I've skipped a slide. So linear transformations are basically the primary functions between vector spaces that we care about in linear algebra. And for the moment, we're going to stick for our examples, we'll stick to linear transformations between spaces of real column vectors. So our vector spaces in mind would be just the spaces of column vectors of a fixed length over the real numbers. So basically, if we have such things, so we have a pair of positive integers m and n, okay, and we have the space Rn. That's the space of all column vectors of length n, whose entries are real numbers. So the space of all column vectors with n entries that are elements of the real numbers. And Rm is the same thing, but with m entries in each column. So what we mean by a linear transformation from Rn to Rm is a function that assigns to every vector in Rn a vector in Rm. So that certainly is something you could have. Like for example, let's say that if n was 3 and if m was 2, so you're talking about R3 to R2. So in R3, we have like 3 coordinate axes, the x, y, and z axis. We can think of the x and y axis as sort of in the floor in a horizontal plane, and the z axis as kind of vertically intersecting that plane. So if you were to go from R3 to R2 and just take every point and throw away its z coordinate, then what you're basically doing is projecting the x, y, z space down onto the xy plane, and you're sort of forgetting about the altitude of each point and just looking at its x and y coordinates. That would be an example of a linear transformation. So they can arise in sort of, in lots of settings. And certainly, geometrically, linear transformations are really important in anything to do with sort of visualization or geometry, including things like animation and computer graphics. So, okay, so a linear transformation from Rn to Rm is a function that takes every vector in Rn to a vector in Rm and satisfies 2 important properties related to the algebraic structure of Rn and Rm. So first one is, okay, we know that Rn is a vector space, and that means that it's equipped with addition and with multiplication by scalars. So if we have a pair of vectors in Rn, we can add them in Rn, just add the coordinates and all the positions, and we have another vector in Rn. So we can take a pair of vectors in Rn, we can add them together in Rn, then apply the function t. Or another thing that we could do is we could apply the function t to the two vectors separately, to u and v, and then add them over in Rm. So here, the second plus sign here, this is addition in Rm. And this one is addition in Rn. And if I scroll illegibly enough here, it'll be impossible to make sense of this note. But the first plus sign is addition in Rn, and the second one is addition in Rm. So they're not the same operation, is the point. Okay, but the point is, if t is a linear transformation, then it means that adding two vectors in Rn together and then applying t to the result should give the same outcome as applying t to the two vectors separately and then adding the results over in Rm. And the second thing that we require is that if we take a vector v in the domain of t, which is Rn, and multiply it by some scalar lambda, and then apply t, we want the outcome to be the same as if we applied t first and then multiplied by lambda. So basically, we want this function t to respect both the additive structure of the vector space Rn and its structure with regard to multiplication by scalars. And again, this is quite typical in mathematics. We care about functions that respect sort of certain properties of their domains, and even within calculus, when you talk about functions from the real numbers to the real numbers, a continuous function is one that basically sort of respects the fact that the geometry of the set of real numbers is a line, and it doesn't break that line if it's a continuous function. So this is something a bit like that. This space Rn has structure with regard to addition and multiplication by scalars, and we care about functions that respect that structure. Those are called linear transformations, and as we will see more and more, they are quite important objects of linear algebra. Okay, what's the connection to matrix multiplication? Well, first observation is that associated to every linear transformation, we have a matrix, and we can interpret the matrix and the linear transformation as being kind of more or less almost alternative representations of the same thing. Not quite, but almost. So to see what that's about, suppose we have a linear transformation from R3 to R2, and it's called T. Okay, we can calculate the image under T of any vector in R3. So a vector of R3 typically looks like this. It's a column with 3 entries. So the assertion is that if we know the images under T of the 3 standard basis vectors, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. So geometrically, you can think about these as being unit vectors pointing along the positive x, y, and z axes. Okay, assertion is if we know the images under T of these 3 vectors, then we can calculate the image under T of anything else. And I guess the reason for that is because we know that ABC, so this is a side note, the vector ABC, no matter what A, B, and C are, this is the vector 1, 0, 0 multiplied by the scalar A, plus the vector 0, 1, 0 multiplied by the scalar B, plus the vector 0, 0, 1 multiplied by the scalar C. So it's a linear combination of those 3 standard basis vectors whose coefficients are the coordinates ABC of the vector that we're looking at. Okay, and we know also that the T is a linear transformation. So applying T to a combination like this is the same as applying T to the 3 parts separately and then doing the addition. And each part of this is a scalar multiple of one of the 3 standard basis vectors. So applying T to the scalar multiple of 1, 0, 0, for example, is the same as applying T to 1, 0, 0, and then multiplying the result of that by A. So what we're saying then is that applying T to the vector ABC it gives the same outcome as if we apply T to 1, 0, 0, then multiply by A, plus applying T to 0, 1, 0 and multiplying by B, plus applying T to 0, 0, 1 and multiplying by C. Okay, so we're saying that the image of a vector ABC under T is a linear combination whose coefficients are A, B, and C of the 3 vectors, the 3 column vectors, which are the images under T of the 3 standard basis vectors in R3, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, we've seen something like this before, a linear combination of column vectors with some coefficients. That is nothing but a matrix vector product. It's the product of the matrix A, whose columns are the images under T of 1, 0, 0, 0, 1, 0, and 0, 0, 1, multiplied by the vector ABC, which is the vector whose image under T we want to calculate. So A here is a 2 by 3 matrix whose columns are the images under the transformation T of 1, 0, 0, 0, 1, 0, and 0, 0, 1, the three standard basis vectors of R3. And what we're saying is, if we want to calculate the image under T of any vector ABC in R3, then all we have to do is take the matrix A, multiply it in front by the column ABC. So we're taking the linear combination of the columns of A, whose coefficients are ABC. So this example, I think, is one that's really kind of worth thinking about in terms of the definition of matrix vector multiplication that we looked at before, and this concept of a linear transformation. So on the next slide, we're going to look at an example of exactly this idea, and also figure out what it has to do with matrix multiplication, which was supposed to be the point of this example, and which I haven't mentioned yet. Okay, so let's look at a particular example then of a linear transformation T from R3 to R2, for which we know the images of the three standard basis vectors. So let's just say, for instance, T of 1, 0, 0 is 1, 2. So that's a vector in R2. T of 0, 1, 0 is 1, 4, and T of 0, 0, 1 is minus 2, 3. Then the matrix of T is the matrix A, which is a 2 by 3 matrix. Okay, so we have a transformation from R3 to R2. Our matrix is 2 by 3, so its number of rows is the dimension of the target space, and its number of columns is the dimension of the domain. And the three columns of A are the images under T of the three standard basis vectors. So 1, 2 in the first column, 1, 4 in the second one, and minus 2, 3 in the third. That's the matrix A. And then if you want to calculate the image under some other vector in R3 under T, so T of, for example, 1, 2, 4, let's say you wanted to know that one, that's given by the product of the matrix A, 1, 2, 1, 4, minus 2, 3, with that column, 1, 2, 4. Okay, what this thing should be, of course, is 1 times 1, 2, plus 2 times 1, 4, plus 4 times minus 2, 3. So exactly the linear combination of the columns of A that's given by this product. So it should be, if we just do the calculation here, we get 1 times 1 plus 1 times 2, that's 3, minus 2 times 4, that's minus 5. And in the second entry, we get 2 times 2 plus 8, sorry, 2 times 1 plus 4 times 2 plus 3 times 4. So we've got 2 plus 8 plus 12, that is 22. So minus 5, 22 is the image of this particular vector under T, if we wanted to know that. Okay, that's how the matrix of a linear transformation defined in terms of the standard basis operates, and we'll see a lot more about this later in the course. I guess something to take away for now is that matrices correspond to linear transformations, and for every linear transformation we can write down a matrix, which becomes a sort of computational tool for calculating images of points under that matrix. But what I wanted to mention in regard to matrix multiplication is, suppose so we have the setup now, T is a transformation from R3 to R2. And just suppose we had another transformation that went from R2 to R2, for instance. Suppose it's another linear transformation. And let's just suppose, to give ourselves a concrete example, that the matrix of this transformation S, which should be 2 by 2 because it's a transformation from R2 to R2, let's suppose that it's 1 minus 1, 2, 0. So this example is discussed in the lecture notes, I should say. It's example 1.2.10 there. Okay, so if you've got these transformations, T that goes from R3 to R2 and S that goes from R2 to R2, then we can take an element of R3 and we can map it into R2 using the transformation T, and then we can apply S. Okay, so we've got this composition. The composition of the functions S and T is a function from R3 to R2. And again, it is a linear transformation. Okay. Okay, I'm supposing that for some vector v in R3, which is the domain of this composition, S after T, okay, this is the function S applied after the function T. I often read this little circle as the word after. I find it it's sort of convenient for remembering what it means. So suppose v is a vector in R3 then. So it's a column with 3 entries. So to apply T to V, we calculate the matrix product. We calculate the matrix product, the matrix vector product AV, and that's a vector in R2. To apply S to this, to this image of V under T, we calculate the matrix product. So B is the matrix of S, so we can calculate B AV. So in other words, we're saying that if we want to apply the transformation S after T to some vector V in R3, that means we're applying S to T of V. This is S of T of V. This is S applied to the matrix product AV, which is an element of R2. And to apply S to an element of R2, we multiply by the matrix B. So this is B AV, which is the same as V multiplied by the matrix BA. So B is a 2 by 2 matrix, A is a 2 by 3 matrix, and BA is their product. So BA is the matrix of the product of the composition S after T, where S and T are respectively the matrices of S and of T. Excuse me, where B and A are respectively the matrices of S and of T. So in our example, we could calculate the product BA if we wanted to, but the point is that matrix multiplication, the operation of matrix multiplication, precisely captures the concept of composition of linear transformations. So in our example, if we wanted to, BA, B was the matrix whose entries were one minus 1 in the first row, 2, 0 in the second. A was the matrix whose entries were 1, 1 minus 2 in the first row, 2, 4, 3 in the second. And so the product of those two matrices will be it'll be a 2 by 3 matrix because it's a 2 by 2 by a 2 by 3. So it represents a linear transformation from R3 to R2, which is S after T. And the first entry we'll have 1 times 1 plus 1 times minus 2, that's minus 1. Second entry we'll have 1 times 1 plus minus 1 times 4, that's minus 3. Third entry we have minus 2, minus 3, that's minus 5. In the fourth entry we have 2 times 1 plus 0 times 2. Or 2 times 1 plus 0 times 4, and 2 times minus 2 plus 0 times 3. So there's the matrix of the transformation S after T. That's the product of the matrices of S and T. So the point here is that matrix multiplication, that operation, precisely captures the operation of composition of linear transformations. So that's another way to think about it, I guess. And it's also a sort of a geometric utility of the operation of matrix multiplication. So it does make sense in terms of, operations that are sensible in terms of the structures of linear algebra. Okay, that's our review of matrix algebra so far. In our next lecture, we'll look at a few more important concepts from matrix algebra, and then we will move on to talk about methods for solving systems of linear equations. So thank you very much, everybody, and see you next time.